Good evening. I'm Andrew Michelson, and I'm a pulmonary critical care fellow here at Washington University, and I'm really excited to share with you our vision for the future of sepsis. As some of you may know, sepsis is an exaggerated set of symptoms that can occur in response to an infection. And when it happens, your symptoms can either be mild, or they can progress to multi-organ failure and even death. And what we know from more recent data is that about 1 out of every 3 inpatient deaths are attributable to sepsis. What we also know is that the incidence of sepsis is continuing to rise. In fact, there's been a more than 2-fold increase in a 5-year period. And with a rising incidence comes a rising cost, now approaching almost $24 billion on an annual basis. And what we know is that early and effective therapy not only can reduce mortality, but it can reduce cost. But treating patients early isn't always possible. And that's because it can be hard to recognize sepsis. In fact, the first clues you may have are that subtle change in vital sign, or that subtle laboratory abnormality that are very easy to miss. And even with the wealth of clinical information available at our fingertips, our best predictors are not able to accurately predict sepsis in a clinically useful way. Machine learning, as we've heard a lot about tonight, is capable of analyzing a lot of discrete data quickly, identifying subtle patterns, and even updating prediction models on a real-time basis. It's no wonder they're starting to be used in multiple sectors, everything from cloud computing to commerce, even to medicine. In fact, there was a recent JAM article that came out, and it basically showed that these computer algorithms are now able to be used in folks who have breast cancer. And it's being able to detect micrometastases more accurately at an earlier stage, ensuring these patients can get the treatment they need up front. So our big idea for you tonight is we want to build a platform that can bring this revolutionary new technology to the bedside to improve outcomes for our patients. And we're already starting to do that by developing some novel algorithms that can predict sepsis at an earlier time point. But we've already started. We're training our machine learning algorithms not only to predict what sepsis looks like, but what it looks like before patients even meet diagnostic criteria. That'll let us identify patients earlier, treat them earlier, and improve their outcomes. Why is now a good time to do this? Well, as we've just seen, the clinical need has never been stronger. New technological innovations have made it easier and more cost-effective to implement than ever before, and we're fortunate enough to work in an environment that favors quality and fosters innovation. To bring this project to reality, we've assembled a really outstanding team of multidisciplinary and interinstitutional leaders. We have physicians, pharmacists, we have computational experts in machine learning, and we even have operational experts to help us bring this to the bedside. So with that, I'd like to thank you for your time, and we invite you to join us with supporting us with a big grant. Thanks so much.
Quick question. What are the theoretical metrics that you're going to track? Are you looking at potentially looking at hemodynamic instability, or what would be a predictor for sepsis that you have in mind? I didn't necessarily get that.
Sure. So the model that we've actually started to build has more than 150 different elements that we're using to predict sepsis off of. There's some research to show that there are some early signs. Big things are being respiratory rate are one of the key factors that people tend to look at. But the respiratory rate is a physiological factor that represents an underlying metabolic change. And so there are some subtle changes that you can look at. And we've explored different ways of looking at these metrics. Is it a min-max? Is it a change from previous value? And things like that. And you can use all of those together to start assessing the true risk factor. So I'd say there's a lot of them out there. We're using a bunch.
And just let me follow, would any of those include real-time assessment and continual assessment, or is it just simply, checking vitals, episodically?
I think you hit on one of the key factors, and the issue with predicting sepsis on the patient is that they're less frequently evaluated than, say, a patient in an emergency department or in an ICU. And so we have to rely on the data that we have. I would love, ultimately, to have a real-time vital sign monitor device that we could track in real time. There are some telemetry monitoring units that have it. Those are closed source, and they don't track every single vital sign, but some of them. But I think ultimately that would be a key piece of information included in our model.
You know, one of the problems with sepsis is, although we talk about that it is problematic, and it is, it's still pretty low prevalence. And so that means even a really great model is going to have a fairly low positive predictive value.
That's around 2 to 3%, so it's pretty low. So if you had a model that just said no every single time, you'd have a 97% accuracy, but clearly that's not actually going to help patients. So what we've started doing is, after we built our, we started using decision trees, gradient boosted decision trees, and after we started doing that, we started clustering our patients so that we can start applying specific models for each individual patient cluster. And this way we can start segmenting out patients that have a higher risk, lower risk, and which models are more effective for those. And that's currently where we're working right now.
And have you seen any outcome on the positive predictive value for those segmentations? What gains have you seen, if any, yet?
We're still working on that, so I don't have that data for you yet. Yeah.
Okay, fair enough.
Questions?
Thank you, Andrew.
Thanks.